Thank you, Kareem, and thank you for inviting me here. We have very close relationships between New York State and Quebec. New York City gets quite a lot of its power from hydropower in Quebec. What I want to do is really give a little bit of background on batteries, then show some of the challenges we have. So at the bottom there I show two electric buses. The one on the right is from a very red state, Alabama. That university is totally electric buses, and the one on the left is electric buses in Hanoi, Vietnam. So let's go back to the beginning. I don't think probably 1/3 of the audience may have been around when the first lithium batteries were made by what was then Esso. We used single crystals in those days, and I'll come back to that again a little later. Those are on the right-hand side, two of the batteries we made, the paperweight we gave away. That particular one is still in my home and still working. So very well-made lithium battery will last forever. Below that is one of the first EV batteries we made. And Exxon was interested in electric vehicles. Remember, there were no computers in those days, no Sony toys and things like that. So a lot of interest in cleaner environment. So this is where we are now. On the left-hand side are two electric vehicles made in the Binghamton area. The forklift truck is Raymond, that's part of Toyota. High-level EVs, below that is BAE Systems. In Binghamton they make all the electrification for their buses, hybrid buses, worldwide. And I'll show you a variety of other vehicles there, including a suite of 4 vehicles London Transport is trying out to see which way to go. And my last trip there, it looks like the hybrid buses are winning out. So tremendous change from the Exxon days, 50-odd years ago, to where we are now. It's in all forms of vehicles. On the grid storage, this builds up a point that was made in the last talk. In the bottom right-hand side, you see the sun, which was shining here this morning, I noticed. And that is a 3.3 gigawatt-hour battery storage facility in the Arizona desert. It is not unique. There's another one just south of San Francisco, also over 3 gigawatt hours. And as mentioned, the sun, solar energy is negative value at the middle of the day. So this is a means of storing that energy and then selling it back when it's needed. Top right is a wind power system. And the bottom there is one of the original grid storage facilities that was again in Binghamton. It was an LFP system made in America by Americans, and what you want to do is get back to that. That particular system worked for about 2 or 3 years. Within 1 month of turning it on, the coal power plant next to it was turned off and never came back on again. And I think most of us New Yorkers are very proud of the fact there's not a single kilowatt hour of electricity generated by coal in New York State today. That particular storage facility then went to Puerto Rico to stabilize the grid after the 2 big hurricanes, and my understanding it may still be working. So again, there's a good grid storage battery will last for a long time. So let me get into a bit of the chemistry, and this is mostly our battery 500 project, and there we're looking mostly at high nickel NMCs, lithium metal, and ether-based electrolytes. So some of you are not familiar with the old Exxon days. We used lithium metal, we used ether-based electrolytes. We've come full circle because ethers played lithium much better than carbonate. But you can see the behavior over the first 5 years of that project. And I said, this is Pacific Northwest National Lab. It's Jay, one of my ex-PhD students. It's her data. And I want to emphasize, this is real data. So most of you reading literature reports of battery storage don't believe what they say, read the fine print. these particular cells are weighed and the volume determined, and that's where the energy density comes from. So you can see over the first 5 years of this project, we both increased the energy density and we increased the lifetime of these cells. And this is with 60% nickel. And with these now meatball morphologies, not large single crystals. Most recent data, you can see the energy density has gone up, and this is published in the Materials Research Society Bulletin last December. We're still pushing on ahead, and some of these cells have got 500 watt-hours per kilogram, and I think you can talk to her to get the latest data and what we're allowed to talk about. But we can do well. It's clearly feasible. I think one of the big issues is what's the charging rate and how safe is lithium metal. So Exxon never had any fires with lithium metal batteries whilst operational, and I understand battery 500 also has had no fires when the batteries are in use. All the fires occurred in batteries either being pulled apart for post-mortems or from just sitting on the bench when things go wrong. So there's an issue at that stage. But this just shows you that we can make high energy density batteries. The question will be, how high should we go? So as we push, maybe I should have gone back to that one, just to emphasize, this is now 80% nickel. If you want to get higher energy density, you've got to go higher and higher nickel. If you go to higher nickel, those materials become more and more reactive. Most charged battery materials are metastable, so they will tend to lose oxygen and give you other problems. So how can you reduce the reactivity of these materials? Two ways: reduce the surface area, go for large single crystals like what Exxon did, and in fact what Sony did for the lithium cobalt oxide initially. Or you modify the materials, you in essence paint the materials just like you paint steel to stop it corroding, so you can paint these materials to make them less reactive. And we've looked at both those techniques. And here are some typical battery electrodes. On the left-hand side, at the top is the original Exxon material. Beneath that is lithium cobalt oxide. This particular picture is one of Jeff Dahm's. And the actual Sony materials are quite a bit bigger than this. Safety was an issue. When Sony first brought these out, they wanted as big crystals as they could possibly get. But then for power, we went to meatballs. That's in the top right-hand side. Worked very well, but obviously issues as soon as we get to very high nickel. Beneath that are now single crystals, and I think Jeff John was a champion of this a few years ago, and now a lot of companies are working on this, and I'll show you a few data in the next slide. This is from one of my ex-PhD students now at Argonne National Lab, and she has shown really that the single crystals behave just as well as the meatballs, and they're much less reactive. The question is, can we make them in a lower cost mode to make them commercially viable? Coating the materials. Now in this slide I show you some 90% nickel, essentially no loss in capacity over hundreds of cycles. So clearly modifying the surfaces of these materials work. But when we talk to large-scale manufacturers, the concern is as soon as you get above 60% nickel, these materials are much more reactive, even when being stored in the facility before making them into batteries. So it's going to cost more money to store them and use them. So there may be a push to push the nickel content down. But I show you there, no niobium. This is niobium stabilized, large cracks in the material. 1% niobium, no cracks in the material, no significantly large ones. So we can modify these materials. Clearly we can go to a higher niobium content. But I really want to go back to LFP. This is becoming in favor today again. for a number of reasons. It's lower cost and the supply chain issue. So on this continent, we have lithium, we have iron, we have phosphorus, and clearly obviously we've got oxygen. So we have all the elements on the continent to make this material and to make it successfully. There's obviously some slight challenges. The material is low energy density. If we switch out some of the iron for manganese, we can increase the energy density. But again, we can do it all here, and there's now a number of companies making the material here in Italy. Hydro-Quebec worked very closely with John Goodenough some years ago on this material. So this is clearly a material of the past, it's a material of the future, and I think you can see more and more of this material being used. The challenge, you'll see there's a nice flat discharge profile, means you don't know whether it's 80% discharged or 80% charged. So we need to do a few tricks to actually measure that. But the real issue we need to address, we wanted batteries, we didn't really care how much they cost to make, but right now the perception is that lithium-ion batteries take about 40 to 80 kilowatt hours of energy to make a 1 kilowatt hour battery. That has to change, that's not sustainable. Some of the materials travel up to 50,000 miles from the original mine to the finished consumer product. That again is not sustainable. What we need really to do is make cleaner, more sustainable batteries and use new technology. Right now we're building gigafactories all over the world, which my colleagues describe as building new old gigafactories. There's nothing in those gigafactories that worked 10 years ago. We have to build gigafactories that make batteries using no toxic materials like NMP, which is almost certainly going to get banned in Europe in the next year or two. It's too toxic to handle. It's the most costly part of a gigafactory. It takes a huge amount of energy to evaporate that off, and then one has to recover all of that material. Also, you'd like to get all the fluorides out so you can get the PFAS out. That's again becoming a real issue. So if we really want to have a clean, sustainable battery industry in North America, we have to do things differently than what they've done now. And clearly, politically, this means we have to, have some protectionism in the first steps of doing this. Obviously, if we can make the electrodes twice as thick, we can cut out half the current collectors, half the separators, but we can't do that with the present materials. They're not highly conductive enough, either for electrons or ions. So we need really to get some new materials and make them much better. So let me just get off some of the science and get on some of the really other issues. This is the circular economy for batteries. It's been discussed already quite a lot today, from the mine to making the materials to the use and then the recycling. And clearly our goal would be to recycle everything, and we're pushing, and I hope the Canadians are doing the same thing. If you make black mass, ban the export of it to Asia. If we've got cobalt here, we need to keep it in North America. But we've got all these elements, we need to address them all scientifically and from an engineering point of view. All of you have heard about valleys of death. Typically, people only talk about one of them. This is the US Department of Energy plot. There are 3 of these valleys of death. One's you can say is in the lab. The next one is commercializing the material, and the third one is it's not much good if you commercialize the material and you then go bankrupt. So you've got to make a profit. So we've got these 3 valleys of death we must overcome, and academia can help do that. So in New York State we've got 3 new programs, and I'll very briefly discuss these to try to address some of these, and this is obviously President Biden's initiative to get some of this happening. So the first effort we had was a very high level, what we call Build Back Better regional challenge from the EDA of the federal government. This was post-COVID. How do we really get industry and everybody else back working again? New York State was very much in favor of cleaner energy. New York State's going to be 70 or 80% clean energy in the next 15 years. And quite a lot of that is obviously thanks to Quebec and its hydropower. But we won this program, basically $113 million. 50 million came from New York State and the other 70 from the federal government, covering all aspects that you need. Key thing that most people don't immediately recognize until you try to make batteries. There's no one on this continent who knows how to make a lithium-ion battery at the manufacturing level. So every gigafactory in this country is basically run by Asians, and that includes Tesla. So we have to really build up a workforce so they can do that. And my gut feel is we're going to have to do that initially by collaborating with the Chinese. We can't just ignore them. The other issue we have in New York State, in Binghamton, Rochester, Buffalo, these were very high-level manufacturing districts. That manufacturing has gone totally away. So what we want to do is really get jobs for those people. So there's huge effort in this Build Back Better to actually hire those people, train them to work in the clean energy industry, where they used to work in Xerox, Kodak, IBM. Most people don't realize IBM started in the Binghamton area many years ago, and their last workers left about 6 months ago. When I went to Binghamton, there were about 10,000 IBM folks there. None of them are there now. So this is what we call the base of our ecosystem. We want to do everything. Because this is New York, it's funded by New York, clearly most of the efforts in New York. But we want to work north of the border. I suspect there are not many US folks here who actually drove to this meeting. I may be one of the few. It's just a short hop up for us, so we want to work with Ontario and Quebec. So this is now the same ecosystem I showed you before. This has now companies for each one of these components. And some of you may recognize Electrovaya is on this plot. Electrovaya is a high-end lithium-ion battery manufacturer based in Ontario. They're building their gigafactory in the west part of New York State using clean hydropower. So by working with these companies, we hope to get everybody involved, to move folks to New York. I said we're very happy to work with Quebec and Ontario to do this. But the point I want to make also is you need the liaison with the public folks, which we do with New York Best and with NatPat. We also, you can't do any of this, you saw earlier this morning, without getting political help. So without our senator, whose picture is there, we would not be doing what we are today. And that's really, I think, important for everybody to remember. Scientists and engineers can't ignore the general public and the political folks all the way from the local to the federal level. So the future trends, is my field, lithium-ion batteries is still going to be there and dominating for the next 10 years or so. 2 reasons. One, they're made in the billions today, so it'll be difficult for anything else to supersede them. But also, they're environmentally probably much cleaner than most of the potential batteries. I was at the Swiss Battery Days in August, and the big concern that almost all flow batteries have a huge carbon footprint. So it's not clear to people that flow batteries are the way to go. And the big advantage of lithium-ion batteries, nothing moves. The person looking after them can be 200 miles away. at the desk. He does not have to be on site. You've got a flow battery, you've got to have people on site there. So I think I will stop there, but I want to make the point is we have to collaborate, we have to work together at all levels, and we welcome collaborations with Quebec, as I said, with just a few miles away. I'll try to answer any questions you might have.